Board, and let's get started with our lecture. So what we're next going to discuss, we talked about ionic bonding from the perspective of Lewis dot structures. What we're now going to talk about is the theory behind covalent bonding. So what is covalent bonding? Covalent bonding involves the sharing of electrons between atoms. Atoms share electrons to form an octet, 8 valence electrons. Now, bonding electrons are shared in pairs between atoms participating in a covalent bond and are counted as belonging to both atoms in a bond. So, for example, in hydrogen, these bonding electrons are counted as belonging to both the hydrogen on the left. So this hydrogen on the left has 2 electrons, and the hydrogen on the right also has 2 electrons. Shared electrons are considered belonging to both atoms that are bonding. So, lone pair electrons, however, as their name implies, also called non-bonding electrons, are electrons that are not shared between atoms. And lone pair electrons are counted as belonging only to the atom containing the lone pair. So for example, for chlorine, so chlorine has a bonding pair of electrons, and it also has a set of lone pair electrons. And in our calculations, even though the bonding electrons belong to both atoms, the lone pair electrons only belong to a single atom. So we have 6 plus 2, or 8 electrons belonging to the chlorine on the left. And then for the chlorine on the right, we have 6 plus 2, or 8 electrons belonging to the chlorine on the right. Lone pair electrons only belong to the atom containing the lone pair, while bonding electrons are counted as belonging to both atoms. Does that make sense to everyone? So if we look at water, for example, H2O, so each hydrogen has a set of bonding electrons. So each of our hydrogens have 2 electrons to their name, while oxygen has both bonding and lone pair electrons. And this oxygen atom has 4 plus 4, or 8 electrons to its name. So all of our atoms fulfill the octet rule, or they fulfill a noble gas-like configuration in the case of hydrogen. Does this example make sense to everyone in terms of counting electrons?
So there's 4, or there's 8 lone pairs? Or no, there's 2?
So there are 2 lone pairs for 4 electrons, and then 4 bonding electrons. So 4 plus 4 gives us 8 in total.
Thank you.
Perfect. So let's keep going through this. And now bonding electrons are shared in pairs between atoms and are counted as belonging to both atoms. Lone pair electrons are counted as belonging only to the atom containing the lone pair. So as we look at water, for example, just to make this water example as explicit as possible, the hydrogens have 2 electrons to their name, while the oxygen atom has 8 electrons to its name. So oxygen has a complete octet, while hydrogen has a noble gas-like configuration for helium. Hydrogen, just as a note, only really wants 2 electrons. So, bonds can also be written as lines between each atom. Each line represents 1 bond or 2 shared electrons. So 1 pair of bonding electrons represents a single bond. So for example, a single bond can be either represented as a line or a set of 2 dots, 2 shared electrons. And as we can see in this example, for fluorine, each of our fluorine atoms have 8 electrons to their name. Does that make sense? So what's important to note is that atoms can share more than 1 pair of electrons and form multiple bonds between atoms to complete their octet. 2 pairs of bonding electrons indicates what's known as a double bond. So in O2, we are sharing 2 sets of electrons. So then each oxygen atom, let me use a different color for that. Each oxygen atom has a total of 8 electrons to its name. We can also represent our double bond using a set of 2 lines. So as you can see, atoms can share. So the question for fluorine, shouldn't it be 10? So if we look at each of our fluorine atoms, we have 6 lone pair electrons and 2 bonding electrons. 6 plus 2 gives us 8. Did that answer that question? Did that address that question?
No, I'm getting a little confused now. Shouldn't fluorine doesn't want to become neon, which is 10? So how come it has 8 electrons?
So the Lewis dot structure depicts the valence electrons. And noble.
Oh, valence electron. Okay, got it. Sorry.
No problem. Yep, and that's why we have 8 valence electrons. You are correct in that neon has 10 total, but in terms of Lewis dot structures and bonding, we're concerned with the valence electron configuration, and in the octet rule, we aim for 8 valence electrons. Does that make sense?
Yes, I missed the 1s2. I missed that 2 electrons. Sorry.
No problem, no problem. So just like we can share 2 sets, 2 pairs of electrons and form a double bond, we can take this one step further and share 3 pairs of bonding electrons and form a triple bond. So in N2, for example, we share 3 pairs of electrons to form what is known as a triple bond. So as we can see, each nitrogen atom has 8 electrons to its name. We can also draw this structure like so. So we can represent pairs of shared electrons or a bond as a line. Now there's one exception that you need to know. Hydrogen prefers to form a duet with 2 valence electrons instead of an octet as it reaches the noble gas configuration of helium. That's why H2, for example, looks a little bit like this, where each of our hydrogens have 2 electrons to their name. We can also draw H2 as 2 hydrogens with a line between them, with the line signifying 2 shared electrons. Does this example make sense to everyone?
Could you repeat, or could you, yeah, go over nitrogen again, how it forms its octet?
Sure. So this nitrogen atom has 6 bonding electrons and 2 lone pair electrons, leading to 8 total valence electrons. Does that answer your question?
Yeah, I just thought it had 7 electrons. Oh, and 2. Okay, never mind, I get it.
I see. You were thinking N2 minus. And that makes, so this 2 signifies we have 2 nitrogen atoms in our formula. And in order to reach an octet, nitrogen forms 3 bonds so that each nitrogen atom with its 3 bonds and 1 lone pair has a total of 8 valence electrons.
Okay,
Does
thank you.
that make sense?
Yeah.
Perfect, perfect. So, before we start talking about drawing these Lewis structures, let's unpack chemical formulas. So chemical formulas specify the number of atoms of each element in a molecular compound. And the subscript, which is this number written in subscript notation, indicates the number of atoms of that element. So for example, COCl3, we know that we have 1 cobalt atom. Note subscripts of 1 are implied. So we have 1 cobalt atom and 3 chlorine atoms because we have a subscript of 3 for chlorine. Does that make sense?
Yes.
So for calcium phosphate, subscripts can also indicate the number of polyatomic subunits or ions. So we know that we have 3 calciums because we have a subscript of 3, but this entire phosphate, PO4 unit, we have 2 of them. So I'm going to write 2 phosphate units. So then how many total phosphorus atoms do I have? How many total phosphorus atoms do I have?
2.
Yep. And likewise, I have 8 oxygen atoms in total. 4 plus 4 gives us 8. Does that make sense to everyone? So the subscripts indicate the number of atoms or polyatomic subunits.
Professor, that says 8. You wrote down 2p and 8. What?
8 oxygens because we have 4 plus 4.
Oh, okay.
Does that make sense?
Yeah. Yes.
Perfect, perfect. So let's do an example where I'm going to count the atoms of each element in the following compounds. So in copper cyanide, I know I have 1 copper, and this 3 subscript applies to everything in the parentheses. So I draw out my 3 cyanide units, and that tells me I have 3 carbons, 1, 2, 3, and I have 3 nitrogens, 1, 2, 3. Does that make sense? So looking at this next example for sodium hydrogen phosphate, I have 2 sodium atoms. I have 1 hydrogen atom, 1 phosphorus atom, and 3 oxygen atoms. Perfect. Any questions on this first example where we're reading chemical formulas? Any questions on this example? Any questions on this example? So let's try And let's work on the following two examples, and let's indicate the number of atoms of each element in the chemical formula. It's really important that you know how to read chemical formulas because this chapter focuses a lot on drawing structures, naming compounds, and writing chemical formulas. So let's work on this example for about 3 to 4 minutes, and we'll discuss this example as a group. Don't be shy to provide your responses in the chat or to provide any questions that you have in the chat or verbally. And we're already starting to see some reasonable responses in the chat for our atom counts. Don't be shy to chime in and share your responses. And we'll discuss this example momentarily. But we're starting to see some reasonable responses in the chat for our proposed atom counts. And we'll discuss this example in about another 1.5 to 2 minutes. Let's try to get a few more responses in the chat and then we'll discuss momentarily. Okay, so first and foremost, let's unpack this first structure. So the 2 applies to every species, every atom in the parentheses. So we're going to draw out our 2 ammonium units. So that tells us we have 2 nitrogens and 4 plus 4, which gives us 8 hydrogens. For chromium, we have 2 chromium atoms. And for oxygen, we have 7 oxygen atoms. For magnesium phosphate, again, the 2 applies to everything in the parentheses. We have 2 phosphorus and 8 oxygens, and we have, wait, let me write this out. I skipped a step. So from the 2 phosphates that we've drawn, we have 2 phosphorus and 8 oxygen, and from our magnesiums, we have 3 magnesium because our subscript is 3. Does that make sense to everyone? Is everyone comfortable with these examples?
Professor, does it matter in what order we write them, like the
No, not
P80?
just
Okay.
as long as your counts are accurate.
Okay, thank you.
Perfect. Any other questions I can address? Okay, so let's keep going now and let's talk about Lewis structures. This is probably one of the most important sections in the early part of this class to set you up for success in the organic portion of allied health. So, Lewis structures allow us to draw plausible, stable structures for a chemical formula. And most stable structures will fulfill the octet rule for each atom. So here's the step-by-step procedure. And don't worry if it seems like a lot at first glance. I just want to have it as a step-by-step guide so you can print this page out if you want and just have it while you're working on problems. So first, you count the total number of valence electrons for all atoms. Next, if you have a cation, you subtract electrons equal to the charge. If a species is an anion, you add electrons equal to the charge. Then you determine the central atom. The central atom is the least electronegative non-hydrogen atom. Then you place your atoms symmetrically around the central atoms. For n equals 1 and n equals 2 elements, you only place a maximum of 4 atoms around the center. And note, there can be multiple central atoms. Now that we have our skeleton, you form a single bond between the central atom and each surrounding atom. And you subtract 2 electrons from your total for each bond formed. Then you place electron pairs around the outer atoms until the octet of all atoms is satisfied or you run out of electrons. Finally, then and only then, if the octet cannot be fulfilled, then and only then you convert lone pair electrons into a double bond or triple bond until the octet is fulfilled. Make sure to check all atoms have a complete octet and only use a double or triple bond if it is actually necessary. I find the biggest error that students make in Lewis structures is they start drawing double and triple bonds before they need to. Okay, now this may seem like a lot of steps, but let's show how this works in practice. So let's look at the following example, CBr2I2. So for carbon, which is a 4A element, how many valence electrons does carbon have? 4. Already you're using a skill from earlier on. Bromine, which is a 7A element, has how many valence electrons? 7. Okay, and how many bromine atoms do we have? 2. So we multiply this 7 by 2. For iodine, it's also a 7A element. So how many electrons does iodine have? 7. And we have 2 iodines. So we have 7 times 2 plus 7 times 2 plus 14, plus 4. That gives us 32 electrons. And you can do this with your calculator. So for our Lewis structure, what should I put as my central atom? What is the least electronegative atom? Comparing carbon, bromine, and iodine. What's the carbon? Exactly. Remember, electronegativity increases going up and to the right in the periodic table. So carbon's the least electronegative. We'll put it in the center. Then I'm going to surround my carbon with my other atoms up to 4. I have all 4 of my atoms and carbon. I have all my atoms drawn out as a skeleton. And now that I have my skeleton, I'm going to form 1 bond each. 1, 2, 3, 4. We then subtract 2 electrons per bond, or 8, and we have 24 electrons remaining. Does that make sense to everyone?
Yes.
Okay, now for our next step, we're going to add our lone pairs. So looking at this iodine, it currently has 2 electrons, 1 bond. How many lone pair electrons do I need to add to get 8?
3?
Yeah, 3 lone pairs or 6 electrons total. So I'm going to add 3 lone pairs for a total of 6 electrons, and that gives me the 8 total I need for a complete octet. So I'm going to do that for both of my iodines. What about bromine? How many lone pair electrons do I need? The same, which would be
3.
3 lone pairs or 6 electrons. The reason why I focus on the electron count is because you count up the total number of lone pairs that you've added: 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 22, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And then we subtract the lone pair electrons that we've used up. We have 0 remaining. We're out of electrons. Is the octet fulfilled? Is the octet fulfilled? I'm just cleaning up the markings. So looking at each of our atoms, is the octet fulfilled for each of our atoms? Let's check. So for carbon, we have 8. For iodine, we have 2 plus 6, which is 8. And for bromine, we have 2 plus 6, which is 8. So have we fulfilled the octet rule for every single one of our atoms in this structure?
Yes.
Yes. Does that make sense to everyone? Does this process make sense? We'll do another example where we have to form a double or triple bond. So let's look. So let's look at the following example. So carbonate. So let's count our electrons. For carbon, we have 4. How many electrons does oxygen contribute as a 6A element? 6, okay. And how many oxygens do we have?
3 or 18?
Yep. And then because we have an anion, we have to add the charge. So what we're going to do is we're going to add 2 electrons to our total because the anion indicates we have 2 extra electrons. That gives us 24 electrons in total. Does everyone see where this adding 2 comes from?
So you add 2 to each oxygen atom. It's not.
No, just to your total. Just to your total.
So wouldn't it be 20?
20 plus 4.
Oh, got it. Okay.
Does that make sense?
Yeah, I was reading it wrong. Thank you.
No problem, no problem. I'm always happy to clarify. So now that we have our electron count, what are we going to put as our central atom? What's our least electronegative atom? Carbon or oxygen?
Carbon.
Carbon, yep. So then we put carbon in the center and we surround it with our 3 oxygens. Then, now that we have our skeleton, we form 1 bond each. We subtract 2 electrons per bond, so 6 in total, and that gives us 18 electrons. Now, where do we place our 18 electrons? Are there atoms with an incomplete octet? Are there atoms that are unhappy right now?
Yes.
Yes. So looking at these oxygens, how many electrons do I need to add?
6.
6, yep. 2, 4, 6, yep. So I'm going to add 6 electrons to each oxygen. So So I've used up 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. I have 0 electrons remaining. So now that I have 0 electrons remaining, looking at this structure, are there atoms with an incomplete octet? Are there atoms with an incomplete octet?
No.
So let's check. So each of these oxygens, I see 2 plus 6, which gives me 8. And as we've noted in the chat, looking at carbon, we only have 6 electrons. And that means carbon doesn't have a complete octet, and carbon's not very happy with this. So what we're going to do is, as we have 0 electrons remaining, I can't just give carbon a lone pair. But what I can do is I can take one of my lone pairs and convert it into a bond. So I'm going to take one of my lone pairs on oxygen and convert it into a double bond. This doesn't cost me any electrons from my total, but it fulfills my octet. So this structure would be the complete structure for carbonate.
When you fill these out, does it matter like which oxygen you choose to add the double bond to, or
It does not actually. And that's a really important point. It doesn't matter as long as the octet for each atom is fulfilled. So as we can see in this structure, carbon now has 8 electrons from 4 bonds. Oxygen, these oxygens with a single bond have 2 plus 6 or 8 electrons, and the oxygen with the double bond has 4 plus 4 or 8 electrons. So we fulfilled the octet rule on all of our atoms, and this would be the complete structure for carbonate. Does that make sense to everyone? Does everyone see how when we run out of electrons and we don't have any more lone pairs to give, we take a lone pair on one of our atoms and we convert it into a double or triple bond? Does that make sense?
yeah. So then you have to add the superscript when you create the structure?
Yes, and the reason why we put this superscript is because we have a charge. We want to show that this structure, this molecule, has a charge. And this is only done for cations and anions, anytime you have a charged molecule. Does this make sense? Yes.
Oops. Just
Please,
to
go ahead.
reiterate, we add the charge because it says 2 negative.
Yes.
So if it were to say 2 positive, we would subtract that charge.
Yes, exactly right. Exactly right. Does that make sense?
Yes.
Perfect, perfect. So Lewis structures are best learned via doing. So they're best done via practice. And this is partially why I like the annotate tool. So I'd like you to try and write the Lewis structures for the following 2 molecules. The first is carbon tetrachloride, and the second molecule is hydrogen cyanide. So let's take about 5 or 6 minutes and work on drawing the Lewis structures for these molecules. And don't be shy to use the annotate tool. If you go to the little black tab under the Zoom options, there'll be this little drop down menu in the tab, and one of the options you can select is annotate. And that allows you to draw your structure, and it allows me to provide feedback. In fact, one of your classmates is already starting to annotate, and multiple students can annotate at once. So don't be shy to share your annotations and share your proposed Lewis structures on the class whiteboard. And don't worry, all annotations for students in the class are completely anonymous. So I can provide feedback once you've drawn it out. And You don't have to worry about your responses being, if you're concerned about presenting in front of the class, don't worry. All the annotations are anonymous, and I really would like students to share their annotations for these Lewis structures so I can provide feedback. You're also welcome to post a picture of your drawn Lewis structure in the chat if that's more convenient. And we'll keep working on this and we'll discuss in about 5 minutes. And remember, make sure to double check the formula to note the number of atoms that you have to work with. So like for hydrogen cyanide, you have more atoms than your formula indicates. And really don't be shy for other students who have access to the annotate feature. Don't be shy to share your responses as well in this class whiteboard. The more responses I have, the more I can provide feedback. And if you have any questions, I'd be more than happy to provide feedback as well. And don't be shy to share your potential responses in the chat or using the annotate feature. Just one hint for the hydrogen cyanide structure, we just have one hydrogen, one carbon, and one nitrogen. So I'll give everyone a few more minutes to work on this example, and we'll discuss this example in about 3 minutes. And if you have any questions, don't be shy to ask. We'll discuss these examples in about 2 minutes. Just to check, how comfortable is everyone accessing these annotate features? So we already see some contributions from one member of our class. Can I get some feedback in the chat? Is everyone able to find the annotate feature? Is everyone comfortable finding and using the annotate feature?
Professor, I don't know where it is. I click on the option, it just says, you know, that black box you told us is original size. That's one option, and the other option is enter full screen, and that's all I see.
Oh, it may be depending on what device you're accessing it from. The annotate feature is commonly available on the PC version for Zoom.
Okay.
Mm-hmm. Yeah, it's certainly hard to write it out, but I find the act of even physically writing something out can really help develop the mechanics and almost the muscle memory in solving problems. So Don't be shy. And I'll also be posting a detailed tutorial on how to use the annotate feature and a supplemental tutorial on that in Canvas later on this week. So let me clear the annotations, and the responses that I saw were great, but let me walk us through once again the problem solving process that I want us to use. So first we count our valence electrons. So for carbon, we know it has 4 electrons. For chlorine, how many valence electrons does chlorine have?
7.
Yep, exactly right. And we have 4 chlorine atoms. That gives us 28 electrons. If we add up our total, 28 plus 4 gives us 32. Now, what atom do we put as our central atom? What atom do we put as our central atom? Carbon, yep. Then we surround our carbon with each of our other atoms. And then, and only then that we have our skeleton, we form 1 bond each. So we've used up 2, 4, 6, 8 electrons. That gives us 24 electrons remaining. Now what do we do? Now what do we do? Lone pairs, exactly. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 0 electrons remaining. Now let's check the octet rule. Carbon has 8 electrons. Chlorine, 2 plus 6 gives us 8. So it looks like the octet rule is fulfilled. Is that correct? Did I do everything correctly when I'm counting? Does this look okay to everyone?
Yes.
Perfect, perfect. So this is the complete structure for carbon tetrachloride. So let's look at another example, hydrogen cyanide. We may talk about this in the context of electron transport, and as cyanide is an inhibitor of one of the central components of the electron transport pathway, which is how we get energy from food and other materials. With that aside, hydrogen has 1 electron to its name. Carbon has 4 electrons to its name. What about nitrogen? How many electrons does nitrogen contribute?
5.
5, exactly right, because nitrogen is a 5A element. We add up our total and we have 10 electrons. So what is our central atom going to be? What's our least
Carbon.
Yep, exactly. So we have carbon, nitrogen, and hydrogen. Then what we're going to do is we're going to form 1 bond each. And I know my method seems pretty boring. Like you may want to skip ahead and draw a triple bond, but trust me, this method has a key benefit in that it's very clear for you to check your work, and it avoids mistakes by making each step very methodical. So now that we have 6 electrons remaining, where do we place these 6 electrons? What atom has an incomplete octet? What atom has an incomplete octet?
Carbon and nitrogen.
Exactly right. And which atom do we place our lone pairs on first? Which atom is more electronegative or on the outside?
Nitrogen.
Nitrogen. Yep. So we're going to take our 6 electrons and we're going to put it on nitrogen. We have 0 electrons remaining. Now what we're going to do is looking at carbon. Is carbon very happy? Does carbon have a complete octet?
No.
No. So what we're going to do is we're going to take one of our lone pairs and we're going to form a double bond. Okay. So we're starting to make some progress, but is carbon happy with this arrangement? Does carbon have a complete octet?
No.
No. So we're going to take our second lone pair and convert it into a triple bond. And that in turn gives us the following structure. So checking our octets, hydrogen has 2 electrons, perfect. Hydrogen has 2 electrons, so that's perfect. Carbon has 6 plus 2, 8 electrons. Nitrogen has 6 plus 2, or 8 electrons. So we fulfilled the octet for all of our atoms, so this structure looks perfect to me. Does this make sense to everyone?
Professor,
Yes.
before I draw like that kind of will that belong like a H and then C and then this, will this belong?
No, that's fine. That's fine. The reason why I draw it linear, like a straight line, is because we'll learn later on in the chapter that a molecule's shape depends on the bonds that it forms. So I always try to, when I'm introducing this topic, I try to draw my structures to lead into and to show the shape. But for right now, in terms of the connectivity and in terms of the arrangement of the atoms and lone pairs and bonds, your structure is perfectly fine. There's no problems with it.
Okay, thank you.
Mhm. Any other questions? So let's keep going now. Let me resize the screen. So remember that hydrogen only wants to form one bond. Did that answer your question in the chat? Did that address your question? Perfect. So let's look at a few more examples. I'd like you to tackle and try and draw the Lewis structure for sulfate, SO3, and selenium difluoride. And we'll discuss these examples momentarily. So don't be shy to share your responses and your proposed Lewis structures for this example using the annotate feature. Or what you can do for each of these structures, A and B, for structure A, you can tell me the number of double bonds that you've drawn. And for structure B, you can tell me the number of lone pairs on selenium. And that way you can share your responses in the chat even if you aren't able to draw the structure using the annotate feature or take a picture. So we'll discuss this example in about 4 to 5 minutes. And I really encourage you to try drawing out each of these Lewis structures so you can compare your problem solving process to my solution and my problem solving process. And if you have any questions, don't be shy to ask it in the chat or unmute and ask your questions verbally. And don't be shy to annotate. The screen can accommodate multiple student annotations. So don't be shy, even if a student is annotating, you're more than welcome to share your Lewis structure as well. And just remember to only form a double or triple bond if you run out of electrons. And the structures look great for sulfur trioxide. So let's try to get some proposed Lewis structures for selenium difluoride. Not exactly a fun compound to make or handle, but nonetheless, it is a very interesting Lewis structure. So let's keep working through this example and let's see a few annotated responses for the formula of selenium difluoride. And don't be shy, there's plenty of space to annotate. And remember, you only form a double bond if you absolutely need to. And only when you run out of electrons. So we see a nice reasonable pool of responses for each of these Lewis structures. I greatly appreciate everyone in the class sharing and participating. And now what I'm gonna do is I'm gonna clear the annotations and we'll discuss each of these examples. So we're definitely on the right track and the improvement I'm seeing looks really good so far. So let's look at SO3, so sulfur trioxide. Sulfur is a 6A element, so it contributes 6 electrons. Oxygen is a 6A element, also contributing 6 electrons. And how many oxygens do we have? How many oxygens do we have reading our formula?
3.
3, yep. So adding up our total, we get 24 electrons. Now, what is our central atom? What's the least electronegative element?
Sulfur.
Sulfur, yep. We place sulfur in the center. We place sulfur in the center and we surround it with 3 oxygens. Then and only then we form 1 bond each. We use up 6 electrons. We have 18 electrons remaining. Now, where do we place our 18 electrons? Where do we put our lone pairs first?
Oxygen.
Yep. 2, 4, 6, 8, 10, 12, 14, 16, 18. We have 0 electrons remaining. Now, sulfur is not very happy, so what do we do? To complete its octet, what do we do?
Double bond.
Yep, we take our lone pair and we convert it into a double bond. That in turn gives us the following valid Lewis structure. And as we see, all of our atoms have 8 electrons, 8 valence electrons. Does this example make sense to everyone? Does this example make sense? If not, let's keep going now. We don't have any questions. So for selenium difluoride, selenium has 6 electrons. Fluorine is a 7A element, contributes 7 electrons, and we have 2 of them. That gives us 20 electrons total. So what's our least electronegative element? What's our least electronegative atom?
Helium.
Yep, selenium, exactly right. So we put selenium as our central atom. We surround it with our 2 fluorines, and now we form 1 bond each. We use up 4 electrons, so we have 16 electrons remaining. Where do we place our lone pairs first?
Chlorine.
Yep, 2, 4, 6, 8, 10, 12. We have 4 electrons remaining. So how many electrons do we give to selenium?
4.
Yep, 2, 4. So now our structure, we fulfilled the octet rule for all of our atoms. So this Lewis structure looks great.
Professor,
Yes.
why can't you just follow another 2 from each fluorine, so get double bond? Each get double bond.
So fluorine, so we want to make sure that we use up all of our valence electrons. And if we formed a double bond, we would exceed the octet. So we want a maximum of 8 valence electrons surrounding each of our atoms.
No, Professor, can I draw?
Yes, please. That structure would have too few electrons. So your Lewis structure should have the same total number of valence electrons, so bonding and lone pair electrons, as the total valence electrons for all of your atoms. So your Lewis structure should have the same total as the total valence electrons for all of your atoms.
Okay, thank you.
Perfect. Any other questions that I can address?
Professor, sorry, I'm a little lost on the F. I had 4 electrons.
For fluorine?
Yes, for fluorine.
For the valence or the Lewis structure?
The Lewis structure.
Ah. So,
Because 2, 4, 6. Um,
so looking at our total, the reason why we have 6 lone pairs is we have 2 electrons from our bond, and then we have 6 electrons from our lone pairs. And remember to count each atom individually. So focus on the fluorine on the right-hand side, count individually, and the fluorine on the left-hand side has 2 plus 6 or 8 electrons total surrounding it. Does that answer your question?
Not really, but let me look over my notes.
Okay, let's do a few more. Let's do another example, and let's see if that can help clarify it. So let's look at the following 2 structures. The first is formaldehyde, and the second is sulfur dioxide. And let's try to draw valid Lewis structures for these 2 molecules. And let's work on this example, and then we'll discuss in about 3 minutes. Sorry, 3 to 4 minutes. And don't be shy to share your responses using the annotate feature. And don't be shy, there's plenty of space for multiple annotations, and the act of sharing your response is invaluable at both cementing the mechanics associated with drawing Lewis structures and visualizing and understanding the thought process behind drawing Lewis structures. And just make sure that your Lewis structure has the same number of total electrons as the valence electrons from all of your atoms. So we'll keep working on this example, and we'll discuss in about 1.5 and 2 minutes. If anyone would like to share another annotation, just so that way I'm collecting a broad range of feedback and responses from the class, I would greatly appreciate it. If not, we'll discuss in about another 1.5 minutes. And it's great that we have a diverse pool of responses to discuss. And let's now talk about these examples. And don't worry, this is a developmental process. I certainly understand that there are a lot of steps that go into writing Lewis structures. And the more practice that we do together as a class, the more comfortable we'll be with this material. This is a really important topic. So the more practice you can do now, the better set up you'll be for the later parts of this class in organic, for example. So for example, let's look at formaldehyde. Carbon has 4 electrons, hydrogen has 2 electrons, and oxygen has 6 electrons. We add up our total, that gives us 12. Which atom do we put as our central atom?
Carbon.
Yep, so we put carbon in the center, we surround it with oxygen and 2 hydrogens, and then we form 1 bond each. Next, we subtract from our total our 6 electrons used for bonding, and where do we place our remaining 6 electrons?
Oxygen.
Yep,
But
2.
why?
The reason for that is oxygen is more electronegative. And as a result, if we're placing our lone pair, we prefer to place it on the more electronegative atom or the outer atom. So we've used up all of our electrons. Now, looking at carbon, does carbon have a complete octet?
No.
So what we're going to do is we're going to take a lone pair and convert it into a double bond. We've now used up all of our electrons, and now we can check. Oxygen has 4 plus 4 or 8 electrons. Carbon has 8 electrons, and each hydrogen has 2 electrons. So we fulfilled the octet rule, and we fulfilled the complete valence shell for all of our atoms. Does this example make sense to everyone? Can I get some feedback in the chat? Is everyone comfortable with this example? Okay, so let's look at this next example for sulfur dioxide. Thankfully, I didn't see any expanded octet examples, but let's start from scratch. Sulfur is 6 electrons. Oxygen is 6 electrons, and we have 2 oxygens. This gives us 18 electrons total. Just like sulfur trioxide, we put sulfur in the center and we surround it with our oxygen atoms. Then we form 1 bond each. So we have 14 electrons remaining. Now where do we place our lone pairs first? What are our most electronegative atoms?
Oxygen.
Yep. So we place 6 electrons each on each oxygen. We have 2 electrons remaining, and we place 2 electrons on sulfur. We're now out of electrons, so how do we complete the octet for sulfur?
Convert the 1 lone pair to
Yep, exactly right. So that gives us the following structure. So key thing, we've used up all of our electrons and the octet rule is fulfilled. Oxygen has 6 plus 2, 8 electrons. Sulfur has 6 plus 2, 8 electrons. The other oxygen has 4 plus 4, or 8 electrons. So we fulfilled the octet for all of our atoms in this structure. Does that make sense? So this initial lecture should provide you, along with the the chapter 2 notes enough of a background to start working on our laboratory report 9, and we'll stop the supplemental lab lecture for today at this time, and you'll be able to use the remainder of the lab period to work on your lab reports, and I'll be available to answer questions for the remainder of this laboratory on your laboratory reports and on any aspects of the homework and practice quiz.